Hi, everyone. Welcome to our first module on Chapter 2. I decided to split Chapter 2 into two pieces because it's a little bit on the heavy side. We're going to start looking at all our sky motion, which is really, really cool, but can also be really tough because, well, everything moves. See, the Earth rotates in a 24-hour period as it revolves around the sun in a 1 year period. But all of that is happening while our sun, remember, is but a tiny, tiny little dot in our galaxy, one of the hundreds of billions of stars in our galaxy. So so we're rotating in a day while we're revolving around the sun in a year. However, our sun with its entire solar system is with its entire solar system is rotating like a galaxy. Our galaxy rotates in hundreds of thousands of years, while our galaxy is in a cluster of galaxies that is also moving. So Earth rotates, revolves around the sun as our sun revolves around the center of our galaxy, as our galaxy moves, and everything moves. So it's a lot. What we're going to do, though, is we're really just going to focus on how does it look from Earth? What are our observations that we make? And we really want to go back and remember that humans have been doing this. We know of it from the earliest recordings. And by recordings, I mean cave drawings. Anything that has recorded history in it has basically shown that folks have used the rotation and the motion and how things appear from Earth as a timekeeper, as a calendar, to track days and nights and times to plant and times to sow and when it's going to get cold and when it's going to get hot. So what we're going to do in this chapter that we're breaking up into two pieces is we're really going to start looking at all of those motions and talk about what happens throughout the day and what happens throughout the night. What happens throughout seasons? What happens throughout, long term, years? And then the next time, the second part of the module, we'll look at other things that affect our motion as well. So remember that as we're doing this, we're really talking about what it looks like from Earth. Because really what we're seeing is a result of the Earth rotating, revolving, but we're going to talk about what does it appear to do when seen from Earth. So let's start here. So remember that right now we're doing chapter 2, but really just focusing on sections 1 and 2 for now. And again, I'm expecting that you have read these sections, and this is not meant to cover all the material that's in the textbook, but it's meant to go more in depth and to clarify. So we're going to talk about measuring and viewing the sky, but again, as seen from Earth. What does the apparent motion of the sky look like? So when we are on Earth, right, we use things like latitude and longitude to give us a sense of direction. Latitude is like a ladder. I climb it to move up and down. So that goes from 0 at the equator, and then I climb the ladder of latitude up to positive 90 degrees at the North Pole or negative 90 degrees at the South Pole. But we also like to talk about longitude, and longitude is what runs east and west. So 0 degrees is at the prime meridian, which, you can find that on a map, and it goes all the way around the Earth, and we divide that as a positive 180 to the east and negative 180 to the west. Now, we don't really need to know this, but we want to see that just like we have on Earth, ways to measure our location using latitude and longitude. We also have that in the sky. So when we look up at the night sky, we want to be able to build a map of our night sky, just like we have a map of planet Earth. And we want to be able to find things in the sky just like we do on Earth. And on Earth, we might use latitude and longitude to find things. Well, we want to build and come up with a way of doing the same thing in our night sky. So the first thing I'm going to talk about is introduce the idea of the celestial sphere. So what is the celestial sphere? The celestial sphere is, well, it's imaginary. It doesn't really exist, but it's like a bubble surrounding the Earth. And think of it as the bubble where all our stars are pasted onto. Now, for us, when we look up at the sky, we can't tell the distances to the stars, but when we look up and we see maybe a constellation here like the Big Dipper, and I'll show you a different view of this. If we see a constellation like the Big Dipper, it appears like every one of those stars in the Big Dipper is kind of a sticker pasted onto this celestial sphere. What we can't see is that all of these stars are at different distances to us. So the first thing is we want to identify the celestial sphere and think of it as the sphere in the sky in which we kind of see all the stars. And what we can't see are their distances. We're going to talk about the Big Dipper a lot because it helps us find north. So this is what the Big Dipper looks like in the night sky. We call it a handle. So imagine that it's a cup that you're going to drink out of. And all of these stars are the handle. And then right in here is the little cup that you're going to serve your water with, the 4 stars that make the cup. It helps us find the North Star because I imagine taking a marble and dropping it into the handle and watching the marble come. It's going to come into the cup. It's going to swing over and it's going to shoot out this way. Oh, hold on. Sorry. Didn't mean to push that just yet. We'll get there. The marble comes in, it comes this way, and it shoots out. And these 2 stars are called the pointer stars, and the North Star would be up here somewhere. I'm going to show you another view of this. But what I mean is about the celestial sphere, when we look up at the sky, it looks like a bunch of stickers, right? All those stars look pasted on to our celestial sphere. What we can't see are their distances. So let's give this little animation where we look at this from a different point of view and see how the stars aren't actually close to each other. They can be very, very far apart from each other. But from our perspective on Earth, it appears that they're together. So this grouping of stars is what we would call a constellation. And really, they just have historical and mythological type of importance. Folks chose to connect the dots in the sky in such a way, and different cultures have different constellations. There's nothing that is really significant about this grouping of stars other than it helps us build a map of the sky, much like continents help us build a map of the Earth. So if we think about our celestial sphere, you see here in the middle, we have our observer, and that observer sees some things. So when they look up in the night sky, hold on, I'm trying to get my pen to work. There we go. Here's our observer, okay, in the night sky. And notice how Earth is right at the center of our celestial sphere. And Earth has a North Pole and a South Pole. And Earth has an equator that cuts it north and south. Well, we can take those same directions and extend them out to this imaginary celestial sphere. It doesn't look like this because all these stars are actually at different distances, but it appears like this from our night sky. So just like Earth has a north pole right here, well, the celestial sphere also has a north celestial pole. And just like the Earth has an equator that divides the northern hemisphere from the southern hemisphere, our celestial sphere has a celestial equator that divides north from south. And we can do the same thing with the South Pole. So a celestial sphere is very much like a globe that we would use for Earth, but it has the stars on it, but it does not take into account the distances to the stars. So let's come back to Polaris and the Big Dipper and why that Big Dipper is so important. Well, the Big Dipper, also known as Ursa Major, is incredibly important because it allows us to find north. It allows us to identify where north is. And if you know where north is, well, then you know where east, south, and west are. So I like to think of the Big Dipper, or Ursa Major, as the pointy part of a compass. You put the pointy part of the compass into your paper, and that's the part that doesn't move. And to make a circle, your pencil goes all the way around. So if we look at the night sky, here is our North Star. It's called Polaris. How did I find it? Let's see. I found the Big Dipper. I found the handle, rolled the marble in, used the two shooter stars, the 2 pointer stars to find the Big Dipper. To find the North Star, Polaris. And Polaris, the North Star, is part of the Little Dipper. So notice how the Little Dipper and the Big Dipper have pretty much the same shape. Polaris, or North Star, is important because it is exactly north for us. It is not a bright star though, so you might not see it in San Diego. It's not very bright, but you can always estimate where it is by finding the Big Dipper and using those pointer stars. Once you find the Big Dipper, and you found the North Star, Polaris, you take that and you drop it directly down to your horizon, and that's north. What do I mean by drop it down to your horizon? Well, what I mean is, so when I look at the Big Dipper, it is up above my horizon. I have to look up. My horizon is flat on the ground like this, but I have to look up. Once I find the Big Dipper, I take my hand and I just bring it straight down to my horizon, because north, east, south, and west are all flat on a horizon. My compass, to tell me directions, has no way of pointing up. It's not going to point up towards the Big Dipper and towards Polaris. So I have to find it and then project it down to my horizon. Okay. So why is the Big Dipper so important? Well, because it allows us to find the North Star. But why? Why is the North Star like the pointy part of our compass? Why is Polaris the point at which nothing moves? If I take a compass, the drawing compass, and hold on, sorry, trying to get my pen to work again. If I take my compass and I, put the pointy part, Polaris, on the ground, on the paper, and I use the pencil to make a circle, indeed, what I'll do is put my pointy part of my compass right on Polaris, and the pencil will make little circles around like this. So Polaris, as the Earth turns, think of the Earth turning as the pencil. As the Earth turns, Polaris doesn't move. Polaris never moves for us. Polaris is always in the same location. So to explain why, let me bring out my little globe here. And I don't know if you can see the whole globe, okay? So a globe is tilted. because our Earth is tilted. And it spins about a certain axis. As I spin it, it is pivoted in the north and pivoted again in the south. There's the south pivot at the south pole, and here's the north pivot at the north pole, and the Earth spins around about those pivots. Now, by pure coincidence, folks, by pure coincidence, there is a star that lines up directly on this north pivot, happens to be Polaris. So imagine that Polaris is in a straight line from this north pivot all the way out into our celestial sphere. And it's very, very far away, hundreds of light years away, but right there by pure coincidence. And it turns out that the Earth's orientation changes every couple of thousands of years, tens of thousands of years. So Polaris has not always been there for us as a central star. It is right now, and that is pure coincidence, but it makes navigation easy. I find Polaris, and I can therefore find north. Okay. So, as the Earth turns, it appears to us that the night sky moves. But it's not the night sky moving, it is Earth turning below it. But to us, it appears as the Earth turns that the sky moves in such a way. So if this is Polaris here, well, there's my northern horizon. And that means that this is east, and that means that this is west. And things rise in the east and set in the west because the Earth turns underneath that celestial sphere. All right, so let's see. Now, when we're in person, I do these in-class questions just as a check to make sure folks are paying attention, to make sure that you've got your vocabulary right. And I usually let you talk to your neighbors. But, well, we don't really have neighbors right now. So think about the question, and when you're ready to answer, I'll give you the answer. So the North Celestial Pole is directly above the North Pole. And where can I find that? That is Polaris is the North Star, and it is part of the Little Dipper, but I find it using the Big Dipper. Okay. And then what cuts the sky into a northern and southern half? So pause it, answer, and then when you're ready, press play again. Well, the celestial equator. Just like the equator cuts the Earth into north and south, our celestial equator cuts our celestial sphere into north and south. So when we're looking at, trying to come up with a map of the sky, we're trying to describe the position as we see it of the sun and the stars and other objects, kind of by where they appear on that celestial sphere. So we want to talk about that North Celestial Pole, which is exactly where Polaris is, the celestial equator, the celestial South Pole. So just like we had those lines of latitude and longitude, we also have something projected onto the night sky that we call declination and right ascension. I am not going to spend too much time on this, but I do want you to know those words. Declination is like our latitude, but in the night sky, and right ascension is like our longitude, but in the night sky. And those are all measured using angular distances. And as a reminder, when you're reading the chapter, if there's a page on mathematical formulas, we're going to skip that. So, what we see in the night sky, what part of the celestial sphere we see, is observer dependent. It depends on where we are. Folks in San Diego are going to see a different sky than folks in South Africa. And it has everything to do with our latitude and where we are. So for some observers, for this top observer, for example, they're directly on the equator. For an observer on the equator, their horizon is a perfect north-south horizon. That means that for them, the North Star is right on their horizon. It's never visible to them. Well, it's visible if it's a very, very flat horizon. But any hill or tree or building, and they can no longer see the North Star. An observer in the southern hemisphere, there's my little observer dude. Little observer dude in the southern hemisphere will never see the North Star. Now, an observer, for example, here, do they tell us where that is? They don't tell us where that is, but that would be like a North American observer. Their horizon is different, so they can see the North Star. It will be above them. Oh, it's at Seattle. Sorry, it's at Seattle, it says. They will be able to see the North Star. Now imagine we have an observer right at the North Pole. So an observer right at the North Pole, the North Star is right above their heads. They will be able to see the North Star. But for an observer on the equator, the North Star is on the horizon. So what folks see depends on where they are. And we're going to come back to this in a bit and talk about this word zenith. Well, there it is. What is the zenith, you're all asking? Well, I have an answer for you. Here is the celestial sphere again. Remember, here's the Earth in the center, and when we look out, it appears as if we're in a bubble with all the stars pasted on it, keeping in mind that in actuality, they're at different distances from us. So the North Celestial Pole is where I would find Polaris. At the South Celestial Pole, there isn't a particular star there. Remember that it's just pure coincidence that the Earth is lined up in such a way that Polaris is in our rotation, right on our axes of rotation, just by pure coincidence. A lucky coincidence for us. So we talk about the North Celestial Pole. That's where our Earth's North Pole is, projected onto the sphere. The South Celestial Pole, that's where Earth's south is, projected onto the celestial sphere. And of course, we can talk about the equator. But right now, I want to talk about this word zenith. So zenith is basically the point right above your head. And guess what? It's yours. And no one else is going to have a similar zenith to yours unless they're standing on your shoulders or, piggyback ride. Your zenith is yours, and it's the point right above your head. And as you move with you, your zenith moves. So what is the zenith? It's the point directly above your head. For people that live right on the North Pole, their zenith would always be the North Star. But for those of us that don't live on the North Pole, our zenith is different. For someone who lives on the equator, their zenith is the equator. So what we see, what half of this celestial sphere we see, absolutely depends on our location. This person has a horizon. Our horizon always cuts in half. We can see everything above that horizon, but we cannot see any of these red scribbles below it for that person's horizon. For a person that lives on the equator, their horizon is here. And they can see a different part of the night sky, the whole part up here, but cannot see these red scribbles. So our night sky, our day sky, everything changes based on where we are. So vocabulary, zenith and meridian. Zenith is the point above your head. That's important. But it's most important because it allows us to define where the meridian is. Well, the meridian is an imaginary line that runs from the North Celestial Pole through your zenith down to the South Celestial Pole. It basically divides the sky above you into east and west. Okay, so the zenith is the point above you, and the meridian is the imaginary line that divides the sky into east and west, and it does so by connecting the North Pole to the South Pole through your meridian. The meridian is important because that's how we define noon, lunchtime. So noon, and I'm going to say apparent noon because there's all these technicalities in astronomy about apparent noon and sidereal noon and solar day and sidereal day, and you can read about it in the textbook. But I'm going to talk about apparent noon because that's kind of what we associate with noon. And apparent noon is basically when the sun crosses the meridian. It happens to be the highest point in the sky. Now, where that is totally depends on the observer. Noontime sun for a San Diego observer is different than noontime sun for an Alaskan observer, and is different than noontime sun for a Quito, Ecuador observer. So when the sun crosses the meridian, we call that noon. And the day is basically how long it takes from the sun when it crosses the meridian to the next time it crosses the meridian. And it's about 24 hours. It's 24 hours. The deviation is very small. Okay, so remember that the meridian is a line that connects north to south. So I'm facing south in this picture here. And it would go kind of above my head and come back behind me as north, but I can't draw that, right? It would come back around you, and north is kind of behind me. But it's the line that divides north to south, so that's my meridian. So right when the sun is on the meridian, that's noon. Remember that things rise in the east and set in the west. So hey, this whole, let's call these let's call these 1, 2, 3, 4, 5. 1 and 2 haven't made it to the meridian yet. Guess what they're called? They are called anti-meridian, before the meridian. Hey, that's AM hours. Anti-meridian, AM, before the sun has crossed the meridian. But 4 and 5 are now past the meridian or post meridian. These are my PM hours. So AM hours refer to when the sun is before the meridian, anti-meridian. PM hours refer to when the sun is post meridian, past the meridian. So that's a little side note about AM and PM. What does it mean? It means the sun is either not crossed the meridian yet or past the meridian. And sun 3 here, well, it's right on the meridian. It's noon. It's lunchtime. So things appear to rise in the east and appear to set in the west. Why? Because our Earth is rotating. Okay, and I'm gonna show you, I'm gonna come back to our Earth here in just a second, but let me finish off with this slide. Just like in the daytime, if I'm looking south, I will see the sun rise east, and I say ish because it doesn't always rise in the same place, and set west-ish, okay, passing through my meridian right at noon. Well, at nighttime, the same thing will happen with the other stars. Remember, the sun is a star. It's the closest star to us. It's our star. But all the stars that we see on the celestial sphere, well, they're going to behave the same way because we're really the ones that are rotating. So things will rise eastish, pass through our meridian again, and set westish. And now this point is midnight. So when we pass our meridian in the daytime, it's noon. When we pass our meridian in the nighttime, it's midnight. So this shows the constellation of Orion. This is Orion the hunter. Here's his belt. Here's a shoulder. Here's another shoulder. He's got a bow and arrow over here. Shows the constellation Orion at midnight. Okay. So I say that stars and the sun appear. They appear to rise eastish, move across the sky through the west, set westish. Except for circumpolar stars, which we'll talk about in just a second. But why? Why does everything appear to move? Well, let's see. Remember, here we go. And I put little Post-it notes. I've got one observer right here, little Post-it note. This is my observer in San Diego. Oh, here it is, in San Diego. Okay. So now imagine that as the Earth rotates, San Diego right now is looking at constellation Laptop. Well, as the Earth rotates, hey, suddenly San Diego can no longer see constellation Laptop. Hey, San Diego is now looking at constellation Dr. Levy over here. Hi. And then as we keep rotating, and now observer sees constellation Laptop again. And all observers are going to basically see the same motion because we're all spinning. We can place our observer, instead of San Diego, we can place our observer. Let's go ahead and place our observer right in Iran. Here's my Irani observer. And that observer, likewise, as the Earth turns, will see constellations rise and set. Right now, they can't see constellation Laptop, but they can see constellation Dr. Levy, and so on and so forth. So things appear to rise. For example, let's come back over here. Think about this observer, cannot see constellation Laptop right now. But suddenly, as the Earth turns, oh, they're starting to see constellation Laptop rising. And then constellation Laptop is right crossing their meridian. And then constellation Laptop is about to set. But at the same time, Dr. Levy's starting to rise. And Dr. Levy's now highest in the sky. And then Dr. Levy sets. And then constellation Laptop rises, passes through the meridian, sets. So that's why all the stars appear to do the same thing. Rise east-ish, move through our meridian in the south, set west-ish, right? And I say east-ish and west-ish because really what's happening is the Earth is rotating under it. Okay, so let's get back to our slides. All right. So I say east-ish and west-ish, and one of the things I want you to do with your project is your observing project is to understand that the sun does not rise in the same location for us and does not set in the same location for us as time goes on. So let's talk about this sunrise and sunset. So the sun rises and sets at different points on our horizon throughout the year. So if we think about our seasons, because we're about to talk about seasons, we may know or not know, but we're about to learn through our observing project that the sun sets and rises at different locations throughout the year. And it doesn't really rise directly east. It doesn't really rise directly east. Hold on, getting my pen again. Doesn't really rise directly east, except for on a very particular day, which we'll talk about. That when it's summer, the sun rises north of east. And when it's winter, the sun rises south of east. So if this is my observing project horizon, and I've marked east and north and south, depending on the time of the year, I'm going to expect the sun at the summer solstice is going to be the northernmost point. We'll see why in a second. And in the winter solstice, it'll be the southernmost point. So if it's rising June 21st, as shown right here, well, maybe in July it's rising here, and in August it's rising here. And oh, maybe in September it rises here, right? So here's September, and then October, November, December. Wait, so the sun is constantly rising between north of east and south of east. And likewise for sunset, except for sunset, we'd be facing west. But it's not going to set directly west. It's going to set north of west or south of west. Well, for us in the northern hemisphere, June 21st is the summer solstice. It is the longest day of the year, and not by coincidence, for the very reason that it is also where the sun rises the northernmost. December 21st is called the winter solstice. It is our shortest day of the year because the sun rises the southernmost. Let's continue down this. Before we understand the rising and the setting, let's talk about our summer solstice, our winter solstice, and our equinoxes. So summer solstice is June 21st. It's the longest day of the year. Winter solstice, December 21st, is the shortest day of the year. So imagine, here we are, we're looking south. And remember, this is our meridian. This is lunchtime. This is my lunchtime sun in the summer. This is my lunchtime sun in the winter. Whoa, they're not in the same spot. In the winter, the sun, remember, doesn't rise east. It rises south of east, moves towards my southern sky, very low on the horizon, and sets south of west. Now in the summer, it rises way over here somewhere, off the charts here, north of east. Takes a very high, large path in the sky, goes very high in the southern sky through my noon, and then sets all the way over here north of west. So clearly, in the winter, the sun is out for less hours. And in the summer, the sun is out for more hours. It's got a larger path to go in the summer. So there's a lot of these interactive simulations that I have embedded into these PowerPoints, but also have into our modules. And if you're reading the digital textbook, there's direct links to that. So let me open this up, and I do want you to play with them. Okay, so here what we get to do is we get to, for an observer in the northern hemisphere, we get to see how the sun rise and set and everything changes through March 21st, June 21st, September 21st, and December 21st. So let's start with our summer solstice here, June 21st, the longest day of the year. And when we press play, we'll see that the sun rose east-ish, then it passes through our meridian right here, and then that's noon, and then it's going to set west-ish. Let's compare that to our December 21st, and let's play. So now notice how it rose much closer to the southern horizon, passes our noon much lower in the sky, and then comes and sets much closer to the southern horizon. Now notice how the stars are doing the same thing. They're rising eastish, going through your local noon, and setting Here we go. And setting westish. Because remember that what's really happening is the Earth is rotating. Now, what happens March 21st and September 21st? March 21st is what we call when spring starts. And September 21st is when fall starts. So in the spring and the fall, the sun rises directly in the east, goes midway up, not as high as the summer, but not as low as the winter, and then it sets directly west. And the stars do the same thing. Notice how our constellations change, though. Now we have different constellations. We'll look at that in a second. Why do we see different constellations at different times of the year? And then let's see, September 21st, that is what we call our fall equinox or autumn equinox. And we'll give all these words. So again, it rises directly in the east, does the exact same thing as it was doing in March 21st, and sets directly in the west. So for a fall semester course, you should, on September 21st in your observing project, if you're doing sunsets, September 21st, the sun sets exactly in the west. If you're doing a spring observing project, then it's during March 21st that the sun sets exactly west and no other day. Well, the 2 days, March and September. So let's look at this a little bit more. I urge you to play with these simulations and really get a feel for them. Okay, so let's think about where the sun is throughout the year. Now I've gone ahead and marked our zenith. Now one thing to note is that for us in the continental United States, the sun will never be at our zenith. Okay, so let's see. When the sun is on our meridian, right, all of this is noontime. But noontime where the sun is changes. So that would be December 21st, our winter solstice, the shortest day of the year, and also when the sun is lowest in the sky. It rose very close to south, so it rose south of east, and it's going to set south of west. It's going to take a very short path in the sky. What day could that be? Let's see. Well, notice how it's not at zenith. Okay, our zenith is up here, but the sun is right there. In the continental US, our sun will never be above our heads. Well, that's June 21st. That's our summer solstice. It's when the sun is highest in the sky for us, but never overhead. You'd have to be on the equator or within the tropics of Cancer and Capricorn, which we'll talk about. So also notice how the sun rises north of east and sets north of west. So if I'm doing an observing project for where the sun sets, throughout the year, it'll set throughout this whole swath of horizon. And throughout the year, it'll rise at all these different locations. And then let's go one more. Let's see, what do we have? Hey, right in the middle, well, this could be either of our equinoxes, our vernal, or March 21st, or our autumnal, September 21st. So now we're starting to connect the motion of the sky to seasons. And notice how right at the equinoxes, the sun rises and sets directly in the east and the west, but only on those 2 days of the year, at no other times. So remember how I said everything moves, and this makes sky motion pretty complex. So right now, we're focusing on the Earth rotating or spinning on its axis. And that axis passes through that north and South Pole. That North Pole would be Polaris. By coincidence, there's a star there. It's called Polaris. And as the Earth rotates, well, that explains for us the rising and setting of stars. Remember our little post-it note, the rising and setting of stars and the sun. It also helps us determine the day from when the sun rises to when it passes through our meridian, noon, and then sets. However, that's not the only thing that the Earth is doing. The Earth is also, at the same time that it's rotating, it is also orbiting the sun or revolving. So the rotation is the day, but the revolving around the sun is the year. And the thing is, they're both happening. It is rotating while it revolves. Oh, yeah, while the galaxy spins and moves, and everything moves in astronomy. So let's look a little bit more at that rotation before I move on to. So I'm sorry, I'm going to be very careful with my words here. Rotation is the day spinning on its axis. Okay, revolving is the orbit around the sun for a year. So rotate is the day, revolve is a year. Okay. So back here, oh, way back here. Hold on, this is going to take a while. Way back here, when we were talking about our North Star, we said, wait a second, this is like the compass point, right? The pointy part of my compass. And as the Earth turns, it appears that things move such that they rise in the east and they set in the west. But wait, not everything rises and sets, because there are stars close to Polaris that never dip below the horizon. We call these circumpolar. So now let me zoom all the way back to where I was and talk about our circumpolar stars. Here we go. This is a time-lapse picture. Okay, so we go out into the desert maybe. We set up a camera with a tripod and we open the shutter. And as we open the shutter, here's our Polaris, our North Star. Well, it's not very centered, sorry. Here's our Polaris, our North Star. What's happening is the Earth is turning underneath the sky. So all of these stars leave these star trails. Imagine one single star is moving in this picture so that it leaves a streak behind. And it's moving, hey, I'm facing north, so that means east is over here and west is over here. And I know things in the east move upwards or rise, and then things in the west move downwards or set. So they appear to make these counterclockwise circles around Polaris. Why? Because the Earth is physically spinning under these stars. So these stars that are close to the Big Dipper, that never rise and set, are called circumpolar. This star here wouldn't be circumpolar. It looks like it just came from below the horizon, and right here it's rising and pops up above the horizon. But this star here would be circumpolar. It started here. As the Earth spins, it moves and moves and moves. It's over here. It's never going to dip below the horizon. If I take a 12-hour picture, it'll be right here. If I could somehow take a 24-hour picture, it would run straight in circles, never rise, never set. These are called circumpolar. They're always going to be close to the North Star. Always. For the south, they're going to be close to the southern pole. For the north, they're going to be close to the northern pole. Okay? So imagine that as these stars move, right? If we leave our shutter open, they leave these star trails in the sky. Now, remember that what we see depends on where we are, right? So these circumpolar constellations never rise or set. They're visible all year, and they appear to move counterclockwise around Polaris. But what we see depends on where we are. So remember that Earth's axis is tilted, right? We don't spin straight up and down. We don't do this. We spin tilted. And it just so happens that Polaris is right there. Okay. That's a coincidence, nothing more than a coincidence. Polaris. And think about an observer. If an observer lives right at the North Pole, their zenith is Polaris. And as they spin around a 24-hour day, the stars will not rise or set for them. If an observer is in the South Pole, well, they'll never see the North Star. But what if an observer is on the equator? And as they move around, because the Earth rotates, they follow this kind of blue path. They go behind and then back over here. Their horizon, let me remove that. Let me clear everything. For an observer on the equator, their horizon is there. They will never see these circumpolar stars. The circumpolar stars are the ones right around here. Okay? Their horizon won't let them do that. So the Earth is tilted, its rotation is tilted, okay? And that tilt is actually incredibly important to us, and it explains a lot of the things that we observe. It explains why some folks see circumpolar stars and others don't. But it's also the main driver of our seasons. So back to our circumpolar stars. What you see depends on where you are. So an observer in Quito on the equator, their horizon is the north and south. So as the Earth turns and all these little circumpolar stars turn around north, they're not going to see them. They're going to be too low on the horizon. But an observer in Seattle, as the Earth turns and they go around, they'll be able to see more and more north circumpolar stars. And an observer directly in the North Pole will see the most circumpolar stars. So for this top observer in Ecuador here in Quito, right on the equator, the sun is going to be really close to their zenith. And in fact, will be directly at their zenith if they're on the equator. Can be at some day of the year. For this bottom observer, the Seattle observer, the sun is way farther from the zenith, and in fact will never be on their zenith. So who can see the greatest portion of circumpolar stars? Folks at the poles, where the North Pole is right above their head, folks at the equator, or about halfway between? Well, folks at the poles. Right? Remember that those circumpolar stars go around the North Pole. So if you're closer to the pole, there's going to be more of them for you. Okay? This is probably a good time to pause this and take a break. Remember that this is meant to be like a full week's worth of material, because we're about to start looking at a different motion that connects the tilt to the revolution around the sun. Okay, so let's talk about the Earth's orbit around the sun. In other words, revolution. And remember that it's going to revolve as it spins, rotation. So the revolution takes a full year. And it's the Earth revolving around the sun and going from this location all the way back to this location takes 1 year. Now, remember that the Earth is tilted. It's super important to always remember that the Earth is tilted. So as we move around the sun, notice that tilt. This takes a year. Okay, so it's going to take about 3 months to go between each of these. So 0, 3, 6, 9, 12, we're back to a year. Okay, so it takes about 3 months for each of those. Okay, now notice how the northern hemisphere and the southern hemisphere, I'm going to draw this in, in red. I meant to do red there. Let's do this in red. I'm just going to expand on their little equator here. They already have the equator for us, but there it is. So remember, we're in the northern hemisphere. Now, when we are in this location here that I've circled, that northern hemisphere is tilted away from the sun. What do I mean? Well, the straight up and down would be this green line, right? That's straight up and down. But the northern hemisphere is not straight up and down. It's tilted away from the sun. Let's look at its opposite over right here. There you go, that one. The straight up and down is right here. And that northern hemisphere is actually tilted in towards the sun. Right? The sun is to the right of the northern hemisphere, and the northern hemisphere is tilted in towards the sun. We're actually going to call this summer for the northern hemisphere. And we're going to call this over here winter for the northern hemisphere. So check it out. One hemisphere is tilted away from the sun, while one hemisphere is tilted in towards the sun. One hemisphere that is tilted toward the sun is experiencing summer. And the one hemisphere that is tilted away from the sun is experiencing winter. Now, does that mean that the northern hemisphere and the southern hemisphere have different seasons at the same time? And the answer is yes. Let's come back to this, the one on the right here. My pen keeps dying, I apologize. Come back over here to this drawing right here on the right. Our northern hemisphere is tilted away from the sun. It's in winter. But wait a second, what's going on with our southern hemisphere? Our southern hemisphere, folks, they're down here. Right? Our straight up and down is over here. And hey, southern hemisphere folks are tilted in towards the sun. They're in summer. And we're going to see exactly how tilting away and towards the sun gives us summer or winter. But the first thing to understand is that as the Earth goes around, that tilt is going to cause some hemispheres to be tilted toward the sun and some hemispheres to be tilted away from the sun. We're going to associate one of those with summer and one of those with winter. Well, what about right here, the equinoxes? Well, the northern hemisphere is not tilted in this way towards the sun, it's tilted to the right. And the sun is towards us. There's no tilt. This and this position are what we call the equinoxes. The sun is tilted neither away, the hemispheres are tilted neither away nor toward the sun, and we call that the equinoxes. Equinoxes, equal days. So we're going to say, hey, hold on. Over here, the northern hemisphere is tilted away from the sun. This is winter. And this is December 21st. After winter, 3 months later, after December 21st, we get March 21st. And this is our spring equinox. 3 months later, we are in June 21st, and we are in our summer solstice. And then September 21st, and we are in our autumn or autumnal equinox. So as we orbit around the sun, we get different seasons because the earth is tilted towards or away from the sun. So in our summer solstice, that northern hemisphere is tilted towards the sun over here. This is northern summer, but over here is southern summer. It is still December 21st. So in the southern hemisphere, December is your summertime. Okay. So again, the summer solstice is the longest day. Remember, the sun sets north of east, goes really high in the southern sky, and sets south of west. It's the longest transition that the sun has. If you live in the poles, you will have 24 hours of sunlight. For the winter hemisphere, that's when your hemisphere is tilted away from the sun. For the northern hemisphere, that's over here, December 21st. For the southern hemisphere, that's over here in June 21st. And the part of the earth that is at the hemisphere's poles will experience 24 hours of nighttime. So for us in the continental US, the sun will never be above our head, and we will also never experience 24 hours of daylight in the summer or 24 hours of darkness in the winter. But in Alaska, you can experience 24 hours of daylight in the summer and 24 hours of darkness in the winter. Now in our equinoxes for equal hours of daylight and nighttime. During our equinoxes, every observer on the earth, doesn't matter if they're at the poles or at the equator, or in San Diego, or in Mexico City, or in the Philippines, or in Australia, they all get equal equinox, equal night and day. 12 hours of daylight, 12 hours of nighttime. The tropics of Cancer and Capricorn are a couple degrees above and below the equator. And they basically mark locations where observers can see the sun at zenith. Okay, it'll happen, for example, in the Tropic of Cancer in the northern hemisphere and the Tropic of Capricorn in the southern hemisphere. So unless you live between the Tropics of Cancer and Capricorn, the sun will never be above your head. San Diego is north of the Tropic of Cancer, and the sun will never be above your head. Okay, before I move into my simulation, let's come back to my globe. Okay, All right. So let's see if I can. All right. So imagine that you all, over here is where the sun is. So as the earth physically revolves, let's see, how am I going to do this? This is a lot easier in the planetarium, folks. I'm sorry. I don't know if you know this, but if we were to be face to face, our classroom would be a planetarium. That's right. The little dome, and I can project things and we can make things move. So I'm doing my best here to show you all of these motions, not using the planetarium. Apologize. So as the earth revolves around the sun, okay, the axis of rotation doesn't change. If the way I'm holding it, it's pointing up and to the left, the way I'm holding it's going to stay that way always. All right. Now, imagine that the sun is over here. So right now, what I see is that folks in the northern hemisphere, okay, here's my zenith. Folks in the northern hemisphere, we don't spin up and down like this. We're spinning like this. And the sun is over here. We're tilted in towards the sun. Now, the sun will be directly over my head if I live on the equator or within the tropics. But if I don't, the sun will never be above my head. However, I am tilted in towards the sun. Northern hemisphere summer. And then the earth revolves, continues. It's also rotating, but it's revolving. And now northern hemisphere is facing that way, but the sun is over here. Okay, so the sun is over here, but now I'm tilted away that way. I'm going to see the sun really low at my feet. Okay, when it's summertime, here's the sun, and I'm tilted in towards the sun. It's going to be pretty high above my head. Not quite exactly above my head. But when it's summertime, now I've moved around, okay? Now the sun is over here, but I'm tilted away from it, so the sun is going to be really low on my feet, really low in that southern sky. So as we revolve around, we're either going to be tilted in towards the sun, right? Or tilted away from the sun, low on our horizon. And if we didn't have tilts, we wouldn't have seasons. Our tilt is what is responsible for our seasons. Okay, so now we get to look at another interactive, which now does deal with seasons. So let's go ahead and pull that one up. Here we go. All right, let's open up this one. Okay, now I want you to also focus right here. I want you to see what happens where the earth is. Not just what's happening in this picture, but also where the earth is. So let's select a date. Let's start, I like the summer solstice, the longest day of the year for us in the northern hemisphere. Now, it doesn't have San Diego. San Diego is about 34 degrees north. Notice how this is 34 degrees south, Sydney, Australia. 90 degrees, well, that's right at the North Pole. 60 degrees north is about Seattle. 19 degrees north is actually my hometown of Mexico City. Viva el DF! So yes, I'm from Mexico City. That's my hometown. San Diego's not on here. But let's go ahead and go to Seattle on June 21st, and let's face south. Okay, so when we're facing south, east is over here, west is over here, but look at, I want you to focus here, okay? The earth is over here, and the northern hemisphere is tilted. Wait, where are we? It's hard to see here. Let's play the animation. Hold on, here we go. Ah, there we go. That's what I was hoping to get. Perfect. Okay, let me pause this. This is exactly what I wanted, a blown up view. Notice how this observer, little orange dude, is tilted in, right? The earth isn't facing straight up. It has that tilt, which for dude, right, dude here in Seattle, it means that he's tilted in towards the sun. And right now, the sun is highest for him, but not directly above head. Okay, he's here. And it's the summer solstice, so the sun is pretty high in the sky. Let's keep going with our animation here. And this whole time, this is actually rotating around so that now he's on the night side, not facing the sun. And then he'll swing back into the day side and then night side, and day side and night side. Okay. Now, for the same observer, let's look at the opposite. Let's look at December 21st. Oh, whoa, the Earth is over here now, right? So let's play this animation. There we go. Okay, let me pause. Now notice how the sun is to the right, but our Earth is tilted to the left. So the northern hemisphere folks are tilted away from the sun. However, our southern hemisphere folks are in summer. Northern hemisphere is in winter, tilted away. Southern hemisphere is in summer, tilted towards. And we see that for dude here in the northern hemisphere, the sun stays really low on that southern horizon. Okay, what's going to happen during our equinoxes? Equal day, equal night. So we go, let me just back up here. Our summer Earth is here. 3 months later, we're going to be over here. So let's go 3 months later to our September 21st. Here we go. And let's play it so I can get a zoomed in. There it is. Hey, dude is tilted to the left, not towards the screen. There's no tilt here, not tilted towards or against. And notice how everyone on Earth has 12 hours of daylight and 12 hours of nighttime. And the same would happen on March 21st. The tilt is going to be, left, right, but the sun is kind of on that other axis, like in towards the screen or out towards the screen. So there's no real tilt. And everyone on Earth is facing 12 hours of daylight and 12 hours of nighttime. So that's for something like Seattle. It's actually probably farther north of Seattle. Let's go to the North Pole. Excuse me. Let's do the North Pole and let's go to summer. Okay. Now, let's play the animation and see what happens. Hey, here comes the sun, and that's noon, but it actually turns out that the sun never sets. And if I could see the animation, it's because as the Earth spins around, the sun just goes around and around and around. So so I can see the animation, let's come back here. The North Pole, as the Earth spins in its 24-hour day, notice how that little red circle stays in daylight the whole time. That is called the Arctic Circle. Anyone above that Arctic Circle is going to be in daylight as the Earth spins around and around. Someone on this path, the Tropic of Cancer, will be in daytime and then come into nighttime. See, the daytime region is lit, the nighttime region is dark. This little red circle, the Arctic Circle, as the Earth rotates around this axis here, it never reaches nighttime. It just goes around and around. But what's happening over in the South Pole, they're tilted away from the sun, and as the Earth goes around and around and around, they never swing into daytime. These folks will. They'll have a long night and a short day. These folks have all night. These folks have all day. So what you see totally depends on where you're standing. Because of the tilt of the Earth, different observers will have different experiences with their seasons. June is not always summer. June is summer for the northern hemisphere, but it is winter for the other hemisphere. Okay. Let me get my screen back up. All right. So when it is summer for people living in the northern hemisphere, it is winter for people living in the southern hemisphere. True or false? The answer is true. The seasons are reversed. So now let's go ahead and look at class question 5. So go ahead and read the question, pause, work your way through it, and when you're ready, come back and I'll work through it with you. So we want to know which of the following is false about the summer solstice. That would be June 21st in the northern hemisphere. Remember that if we were in the southern hemisphere, June 21st would be the winter solstice, and the summer solstice would be December 21st. But here we're in the northern hemisphere, so it's June 21st, the summer solstice. And we want to know which of these statements is false. So I'm going to go through each of them and label them as true or false. So summer solstice, it is the day with the longest amount of sunlight. That is true. That is our definition of the summer solstice. The summer solstice, is it when the sun crosses the meridian? So what happens at meridian, that's noon, crosses the meridian at a point closest to zenith. That's when it's going to be closest to overhead, is what this statement is saying. Is the sun closest to, above our head at noon on the summer solstice? That is also true. It is closest to the horizon in the winter at noon and closest to above head in the summer at noon. Is the summer solstice the day when the sun rises furthest to the north on the horizon? Well, that is also true. Remember that in the summer, the sun rises north of east and sets north of west. So all of these are true. And remember to come back to, if we're looking south, then west is over here, east is over here. And, we've got our winter sun is close to the horizon. Our equinox sun sets and rises right on east and west. And our summer sun goes very high in the sky and rises north of east and sets north of west. And our zenith would be up here somewhere. Okay, then our horizon is down here. So in the winter at noon, it is close to the horizon. In the summer at noon, it is close to our zenith. Okay, but we haven't finished answering this question yet. So let's see. We're looking for which of these statements is false, right? So they all seem to be true, and now we need to be careful with the way our wording is, that they're all true. So let's go back and read this. Are all of the above false? No. Are none of the above false? That's correct. So our answer here is E. None of the statements are false. They're all true. Okay? So our correct answer is E. So we're starting to talk about seasons, and we can see how being tilted in towards the sun means that we're going to get more daylight hours. And if we're in the Arctics, we might get 24 hours of daytime. And how that has to do with the tilt and with moving around the sun, our revolution. But we want to ask ourselves, what really causes the seasons? So I'm going to run through some common misconceptions. There's a misconception that the seasons are due to distance from the sun. In other words, when we're closer to the sun, it's going to be summer. Why would we think this? Well, we've known throughout our whole lives that the closer we get to fire, the hotter it is, right? So clearly it's summer, it's hot, we must be close to the sun. Well, the truth is that even though the distance between the earth and the sun varies throughout the year, we're not in a perfect circle. That change in distance is pretty small, and it doesn't have a significant effect on our climate. And let's go a little bit further. Wait, when it's summer here in the north, what's happening in the southern hemisphere? It's winter. So could I say, because the earth is closer to the sun, it's hotter? Well, but the folks in the southern hemisphere are going, hold on, but it's winter for me. So that doesn't make any sense. And when we're farther from the earth, from the sun, that means, the farther I am from fire, the colder it is. It's colder, it's winter. But the folks in the southern hemisphere would say, no, I'm in summer right now. Well, one thing to note is that, in fact, the earth is farthest from the sun. The earth is farthest from the sun in July. That's when it's farthest from the sun. That's when if this argument is true, if this hypothesis is true, if the hypothesis is the closer we are to the sun, the hotter it is, this observation would make us rethink our hypothesis. We're actually closer to the sun we're actually farthest from the sun in July. We're closest to the sun in December. So that can't be it. There must be another factor. Now I'm thinking it has to do with tilt, because wait a second, when it's summertime, I'm tilted in towards the sun. When it's wintertime, I'm tilted away from the sun. Okay, my sun is over here. When it's summertime, I'm tilted in towards the sun. When it's wintertime, I'm tilted away from the sun. Maybe that's it. Maybe it's not distance. So there has to be another factor. Clearly can't be distance. Okay, let's see. Well, what about daylight hours? The more daylight hours I have, the hotter it's gonna be. Is that it? There must be another factor. Why? Well, because when we live at the poles, when we live in Alaska, in the summertime, we have 24 hours of sunlight, but it's still not very hot. It's way hotter at the equator. It's way hotter in San Diego, where we don't get as many sunlight hours. So that can't be it. There has to be something else. Well, what if it's how direct the sunlight hits? I think this is it. So really, what truly affects our seasons and why summer is hot and why winter is cold is not because of distance, because then different hemispheres having different seasons couldn't be explained. It's not because of number of daylight hours, because then I would expect the poles to be the hottest during the summer, and they're not. So what if we think about how direct the sunlight comes? So remember that in the winter time, that hemisphere is tilted away from the sun. So the sun kind of is like hitting low in that southern horizon, low on your feet. Sunlight comes in at a very big angle. It doesn't hit very directly. It kind of spreads out and hits. During the summertime, the sun is much higher in the southern sky. We're tilted in towards the sun. The sun is very high in the sky, and those rays kind of come and make a more direct hit. In the winter, the sunlight comes at such a low angle that heat from the sunlight gets spread out over a large area. When the sun is high in the sky, like in the summertime, that heat from that sunlight gets more directed, more focused into a small area. And truly, this is what is causing the changes in climate and weather between our seasons. When it is wintertime, that hemisphere is tilted away from the sun. December 21st for the north, June 21st for the south, and that sunlight comes in very indirectly and it gets spread out over a large area. So that's winter and coolness. I don't get to keep all that energy, it gets spread out. In the summertime, high sun, very direct sunlight, so it gets concentrated on this small area, and that's summer. And remember that it has to happen at opposite hemispheres at opposite times. So when do we have the greatest direct sunlight? And the answer would be, well, during the summer. That's when we're tilted in. That's when we're tilted in towards the sun, and the sunlight is most direct. Next question, I'll give you some time to read it. Pause, think about it, and when you're ready, unpause. So we've kind of gone through all of these and talked about, are they significant or not? Does the hypothesis hold after we've tested? So could it be changes in the number of daylight hours? Is that a significant factor in the cycle of the seasons of the earth? It's not, because in Alaska, you can get 24 hours of daylight in the summer and it's still really cold. So this is insignificant. Insignificant. What about variation in the directness of sunlight? Actually, that's pretty significant. That's what causes the difference. When it's direct, it's that direct hit, all that energy concentrated into a small area, it's hot. When it's indirect, it comes in at an angle and all that energy gets spread out and it's not very hot. What about the distance of the earth and the sun, the distance between the earth and the sun? Well, again, when we're closest in December, which is a southern summer, but that's a northern winter. So distance doesn't affect anything at all, because the south in the southern hemisphere, they're hot, but in the northern hemisphere, it's cold. So it doesn't matter at all. This is actually the most insignificant of all of them. The changes in daylight hours, it is insignificant, but it does also explain the difference between, June 21st weather versus, say, March weather. Okay. So I would say that the least significant factor would be C, the distance from the earth, because it has completely opposite effects in the northern hemisphere than in the southern hemisphere, and it's such a small change that it practically doesn't exist. So the answer is C. Okay. The most significant is B. That's the most significant. Okay, next. Now this is a question that I'm actually asking you before I give you the slides. And again, it's a reading check. It's a reading check. Okay. So we're going to read it. We're going to pause it. And you're going to write down your answer. But then I'm going to go look at the slides and then we'll come back and make sure we answer it. Okay. So if Earth's rotation was not tilted, in other words, if the rotation were straight up and down, what would happen? Okay. So we'll have to come back to this. The reason we have to come back to this is because we have the word ecliptic in there. Well, what is the ecliptic? some vocabulary that we have to learn, right? Polaris is the North Star. The zenith is the point above your head. The meridian connects north and south through your zenith. What about the ecliptic? The ecliptic is where we say the apparent location of the sun in the night sky. In other words, as we look out into the sky, in which constellations does the sun appear to be in that day? Now, they happen to be the constellations of our zodiac. And I do spend some time on the difference between astrology, a pseudoscience that makes broad, very broad claims that basically most anyone can identify with, or astronomy, which is an exact science. So astrology says something like this: on the day you were born, the earth and the sun were in such an orientation that, for example, the earth, let's say you were born in October, and well, actually it's not October, but okay. On the day you were born, this is where the earth was in its revolution around the sun. Okay, this is where the earth was. And as we look up into the sky, it would appear that the sun is in the constellation of Scorpio. So someone born on this day when the earth was right here would be a Scorpio horoscope. Some other time later, now the earth is over here. Okay, and the earth is over here. When we look up, the sun appears to be in the constellation of Aquarius. You must be an Aquarius. Now, one of the major problems with astrology is that's not true anymore. Someone born in late October and early November is said to be a Scorpio. I was born in late October. I won't tell you what year. It was a long time ago. But I've looked up where was the sun when I was born, and it's actually not in Scorpio. Over hundreds of years, the orientation of the earth and the sun and the night sky has shifted. When astrology was first born, sure, that might have been the case, that the sun appeared to be in Scorpio in late November and early October, but it is no longer. The sun no longer appears to be in Scorpio in late October and early November. So take that with a grain of salt, okay? But let me get back to the ecliptic. So the ecliptic is the position of the sun as it would appear, right? This day where the earth is here, we would look up and we would say, hey, the sun is in Scorpio. And then a month later, it would be in Sagittarius, and then Capricorn, and then Aquarius, and then Pisces, and then Aries, Taurus, Gemini, Cancer, Leo, Virgo, Libra, back to Scorpio. What's really happening is the earth is moving around. So the ecliptic is the apparent path that the sun takes in the sky. The ecliptic, okay, because the earth is tilted, the ecliptic is not on the equator. I like this picture a little bit better. So think about a couple of things that are happening, okay? One of the things that is happening is the earth is on its 365-day journey, its 12-month journey around the sun. And so it completes a full circle every 12 months. So on January 1st, the earth is in this location. February 1st, it's going to have moved. March 1st, it'll have moved more. And on January 1st, we'll come right back again. Okay, so if that's January, we're going to be over here in June. Okay, all right, so let's look at, all right, here we go. Let's say, what do I see? Let's, hold on, I'm sorry, I'm playing with my pen. This is very distracting, I apologize. Let's place ourselves in our January location. Okay. This is long-term motion of revolution around the sun. It takes a month for the Earth to move from its January location to its February location. What do I see in one day, one rotation? There's going to be times where I'm on the day side, and there's going to be times where I'm on the night side. In one day, this little Earth globe is going to spin around in 24 hours. So in this day, when I am right here and the sun is highest in the sky, that's noon. At noon, I would look up, and if I could, I would see that behind the sun is Sagittarius. So in January, Sagittarius is a daytime constellation. I do not expect to see it. Now, as the Earth rotates, now I get over here. Hey, now I'm on the midnight side. Okay, this is noon, and this is midnight. I'm on the midnight side. I look up in my night sky, and what do I see? I see Gemini. So in January, Gemini is up at midnight. And they would say that you are a Sagittarius because the sun was like in Sagittarius on that day. Okay. What about, let's go say to like March 1st. So now March 1st, and we're over here now. And in 24 hours, we're going to rotate around, but we're on the noon side. We look up and we see the sun in Aquarius. And when we're on the midnight side, we see the constellation of Leo. Right, so we're seeing different constellations at midnight. Well, what happens when it's June? When it's June and the Earth is over here, now our sun is in Gemini, and our midnight is Sagittarius. Wait, so I can't see Sagittarius at night in January. It's a daytime constellation, but I can see it in June. So in June, I might be able to see these constellations. These are summer constellations, but my winter constellations are the ones over here. So in the winter time, I expect to see nighttime constellations of Gemini, Taurus, Aries. In the summertime, I expect to see nighttime constellations of Capricorn, Sagittarius, Scorpio. Okay. And remember that over time, these alignments have changed so that the sun is not exactly in the house, as the astrologers would call it. And moreover, there's another constellation right in here that actually makes it a 13-month horoscope rather than a 12-month horoscope. So that doesn't match either. And it makes very broad generalizations that really can't be tested with the scientific method. So this picture of the ecliptic, right here it is, the projection of Earth's orbit onto the night sky right here, the projection of Earth's orbit. But really, it seems to us like that's the path that the sun takes in the night sky. The sun passes through these particular constellations which are our zodiac constellations. They lie on the ecliptic. So in our summer sky, we might be able to see Scorpio and Sagittarius. But in our winter sky, we won't be able to see them. Instead, what we'll see is Orion and some other ones like Lepus and Canis Major and Canis Minor. Scorpio is a cool one because it's kind of once you learn to identify it, you can kind of see it because it has the really cool stinger. You can always kind of see this little stinger back here. Sagittarius is equally as cool because it looks like a teapot. Sagittarius is the teapot, right? It looks exactly like a teapot. And most important, you see the steam coming out of the teapot? That's actually an arm of the Milky Way galaxy. We'll talk about that later. So think of Sagittarius as the steam pot, and the steam coming out of it is an arm of the Milky Way galaxy. In fact, the center of the Milky Way galaxy is right there. So if you can find Sagittarius in the night sky, look in the summertime, not in the winter. You can find Sagittarius if you can see where the steam is coming out of the teapot. You now know where the center of our Milky Way galaxy is. And I think that's pretty cool. Okay, so we've done a lot in this topic. This is 2 sections of the book. I recommend that you read very carefully the book, that you study those figures, that you try to get yourself a model, right? You don't have to go out and buy anything, but like, put a toothpick in an orange, whatever works for you, and kind of work with what happens when we rotate, what happens when we revolve, the business with the tilt, and then all of our vocabulary that we have. So we started by saying the sun doesn't really rise east, it rises east-ish. And it doesn't set west, it sets west-ish. And the only days that it rises exactly east and sets exactly west are on our equinoxes. Equal day, equal night. We have 12 hours a day, 12 hours a night, because the earth is oriented like this, tilted to the left, and the sun is kind of on the foreground. So everybody gets 12 hours a day, 12 hours a night. Our summer is now when we're tilted in towards the sun. So the northern hemisphere has the sun closer to the top of their head, more direct sunlight and more sunlight hours. The sun rises north of east, takes a very large path high through the southern sky, and sets north of west. Then we keep, revolving around the sun. We hit the other equinox where we're also not tilted towards and away. Everybody gets 12 hours a day, 12 hours a night. And then as we continue on our revolution, there's going to be a point where the northern hemisphere is, so this is my sun over here, where the northern hemisphere is tilted away from the sun. The sun is going to be low on my feet, right? Low on my horizon. It's going to rise close to the south, hug, really close to the south, and then set close to the south. It takes a very small path in the night sky, in the daytime sky. So our winter, the sun is a very short path with very indirect sunlight, because we're tilted away from the sun. In the summer, the sun takes a very large path in the sky with very direct sunlight because we're tilted towards the sun. Okay. Please, please, please come meet me in office hours. Send me a message if you can't make it. I'd love to get to know you and chat about things and a lot of cool stuff that I'm, not really talking about in this class. But if you've got questions, or if you have questions about this stuff, it's not easy. All this motion can be really complex. And one of the great advantages to being in face-to-face is the use of our planetarium. But you know what? We do the best we can. and this is what we're doing, and you're doing great. So please come talk to me, ask me questions, check in. Make sure you're reading the textbook. Make sure you're playing with those simulations. You're making notes, and then you're contacting me in office hours. I'll come back with next lecture will be the second part of chapter 2, the following sections of chapter 2, where we start to tie in more things to this motion. So I hope you're looking at your observing project and you're marking on your horizon, and you know, have an idea now of which way you expect the sun to move based on the tilt and what we just learned today. So make sure you keep up with that observation, and check in with me. All right, bye folks.